Hello, this is the Chapter 10 lesson. In this lesson, we're going to talk about a general class of hypothesis test called non-parametric tests. And so to start off, let's briefly review what we talked about in Chapter 7. Chapter 7, we talked about a whole bunch of different hypothesis tests, and we had several that dealt with tests about a population mean, such as the t-test, or the two-sample t-test, or the paired t-test, or ANOVA. Now, in all those tests, we stressed the fact that they had requirements such as the populations are normally distributed or the sample sizes are large, large meaning greater than 30. And so because these hypothesis tests had requirements about the distribution of the population, we call these tests parametric tests. In this chapter, we're going to talk about kind of the opposite of a parametric test, and that's a non-parametric test. What makes a non-parametric test is that it does not have a requirement about the distribution of the population. Specifically, it's not going to have the requirement that the population be normally distributed. Now, a couple of advantages of non-parametric tests is that many of them are relatively easy to perform. Many of them simply involve counting data values. Now, some of them are a little more complicated, but some of them are extremely simple. And the second advantage is the real big one, is that in all of them, the population distribution does not matter. We're not going to have a requirement that the population be normally distributed or have a binomial distribution or have any other sort of distribution. Okay? Now, a disadvantage of non-parametric tests is number one, that they often waste information. And we'll illustrate what we mean by that when we talk about the sign test. Another disadvantage is that non-parametric tests typically have lower power than a parametric test. Remember, the power of a test was like the probability of rejecting a false null hypothesis, or in other words, it's the probability or likelihood of detecting a difference. Non-parametric tests aren't quite as good as detecting differences, so they have a lower power. Another thing that we're going to talk about in this chapter is a couple of different ways of doing hypothesis testing. And we've kind of briefly mentioned these methods before, but so far in our lessons we've only used one of these methods. In this section or this chapter, we're going to start using the other method as well. And so in all hypothesis tests, in the end, we come to a conclusion of either reject the null hypothesis or do not reject the null hypothesis. We often call this the technical conclusion. And then based off of that technical conclusion, we came to a final conclusion. There's kind of two different methods or two different approaches for coming to that technical conclusion. The one that we've always used in the lessons is called the p-value method, where we calculate a p-value, which is a probability, and then we compare that to the significance level, which is typically alpha equals 0.05. In the other method that we call the traditional method, or maybe the critical value method, and this is the method that the book often used, is where we compare the test statistic to a critical value, and then we either reject the null hypothesis or do not reject it based on whether the test statistic is larger than the critical value or less than the critical value. And so in this chapter, we're going to start doing some traditional method hypothesis tests. We will have one that's done with a p-value, but most of them are going to be done with this traditional method. So to illustrate the need for a non-parametric test and what we mean by this normality requirement, let's take a simple example. Suppose we are testing a new pain medication, and so we give the medication to some patients, and then the patients rate the symptom improvement on a scale of 1 to 5, where 1 means no reduction and a 5 means a great reduction. And so let's define a parameter here, mu, to equal the mean reduction. Now let's suppose that a researcher claims that the mean reduction for this pain reliever is greater than 3. And so they set up hypotheses that mu equals 3 versus mu is greater than 3. And so we test hypotheses like this back in Chapter 7, And so we used either a z or a t-test. A z-test if our sample was large, and a t-test if our sample was small. Well, let's suppose that we give this drug to 17 patients, which is a small number of patients. And this histogram here summarizes our results. So in one patient, they had a level of reduction of 1. So it didn't work very well for them. In 2 patients, they had a reduction of 2. In 3 patients, they had a reduction of 3. In 6 patients, they had a reduction of 4. And in 5 patients, they had a reduction of 5. So there's a histogram of our data. Okay. Now, notice the shape of this bell curve, or the shape of this histogram. Remember, the shape of the histogram indicates the distribution of my data, or is an estimate of the distribution of my population. A bell curve shape indicates a normal distribution. A non-bell curve shape indicates something other than a normal distribution. Well, this doesn't really have much of a bell curve shape. A bell curve should increase to a max and then decrease down to a low again, but it never really gets low. And so because we do not have a bell curve shape, that's an indication that my population is not normally distributed, so I don't meet my requirements for my t-test. And so that means we've got to do something else to analyze our data. Our requirements for our t-test are not met. So that something else that we're going to do is a type of non-parametric test. And in this chapter, we're going to talk about 4 different types of non-parametric tests. There are many more out there, but we're just going to talk about 4 of them. The first is the Mann-Whitney U-test. The second is the sign test. The third is the Wilcoxon signed rank test. And then the fourth is the Kruskal-Wallis test. Okay. Now, these tests are formally tests about population medians. They're not tests about population means, as we talked about in Chapter 7. So these tests are not going to be identical to what we talked about in Chapter 7. They are, however, going to be very similar in the sense that a median is very similar to a mean. Not exactly the same thing, but a similar idea. So medians, it's been a while since we've talked about medians, so let's briefly review the idea of a median. Back in, I think it was Chapter 4, we defined a sample median, and here's kind of a informal way of defining a median, or how to calculate a median. So a sample median is we collect sample data, and then we line up the data in the sample from smallest to largest, and we take the value right in the middle. So a median is like a data value that's right in the middle. It's bigger than 50% of the other data, and it's less than 50% of the other data. Now, a similar idea is the population median. And to find a population median, we would line up all the values in the population from smallest to largest and take the value right in the middle. So the difference between a sample median and a population median is where the data come from. If the data come from a sample, then the median is called a sample median. If the data come from every single member of our population, then the median is called the population median. Now, it's virtually impossible to calculate a population median because we would need to get data from every single member of our population. That's virtually impossible to do. And so we want to know something about a population median. We're going to go out and collect data from a sample, calculate a sample median, and then we're going to use a non-parametric test in order to make some conclusions about the value of that population median. So our first type of non-parametric test is called the Mann-Whitney U-test. Mann and Whitney are the 2 statisticians that came up with this type of test, or at least who are credited with it. And the purpose of a Mann-Whitney U-test is to compare the medians of 2 independent populations. And so this test is very similar to this 2-sample Z or t-test. In a 2-sample Z or t-test, we compared the means of 2 independent populations. Here in this Mann-Whitney U-test, we're going to compare the medians of 2 independent populations. And so in a Mann-Whitney U-test, the formal hypotheses that we're going to test are, or the null is that the 2 population medians are equal, and the alternative is that the two population medians are not equal. Now we're not going to define any parameters here. We could define a parameter to represent the median of the first population and the median of the second population, but I don't think that's really necessary. So we're just going to state our hypotheses in words here. The null is that the populations are equal, and the alternative is that they are not equal. Okay. Informally, we could state these hypotheses as the null is that the two populations are equal, and the alternative is that the two populations are not equal. I think this is the way that the book states the hypotheses, but really these are claims or hypotheses about population medians. Now, one comment here about a Mann-Whitney U-test is that this is always going to be a two-tailed test. Now, we can see it's a two-tailed test because of the not equal to term here in the alternative hypothesis. So we're not going to have a one-tail versus two-tailed test. These are always going to be two-tailed tests. So to illustrate an application of the Mann-Whitney U-test, let's look at example 10.1 from the textbook. And what we're doing in this example is comparing a new asthma drug to a placebo. So this is a very similar scenario to what we've done before in different contexts. And in our data we have a total of 10 participants, and each one of those participants records the number of episodes of shortness of breath over a 1-week period. Okay. And so here's our data. So the first patient on the placebo had 7 episodes, the second had 5 episodes, so on and so forth. The first person on the drug had 3 episodes, the second person had 6 episodes, so on and so forth. Okay. So notice that these sets of data are rather small, and so whenever we have real small sets of data like that, that's an indication that we might want to use a non-parametric test. And we'll kind of summarize that idea at the end of this lesson. Okay. And so the question that we want to try to answer is there any difference between the two treatments? So informally, the hypotheses that we're going to test are that there is no difference between the treatments versus there is a difference.